This is our first chapter for gas metal arc welding and flux-core arc welding. This is our basic semi-automatic welding processes class. It's Weld 1770, and we're going to start in chapter 21. That's on page 747 in your textbook, so if you want to turn there and find that page, I actually want to begin on the next page, 748. Gas metal arc welding. It's a little hard to see, but this is a picture of gas metal arc welding being done in a fabrication shop, and you can see a couple of guys down here fabricating some kind of a grid pattern. Here's their equipment over there. And you can see this is a long boom, and the boom actually suspends the wire feeder from above them. And this is just one way that you can set these things up. Of course, in our lab we have the wire feeder sitting on tables, but this is an option. And it makes it pretty convenient when you have to work in the middle of something that you can't otherwise get to. So I wanted to point that out, particularly to point out that equipment to you. Now, looking at page 748, I'm beginning in the second paragraph in the first column, which reads, the complete name for gas metal arc for GMAW is gas metal arc welding. That's a bullet. You should understand that. Slang and trade names are often applied, such as MIG for metal inert gas, and MAG, metal active gas. That would be your reactive gases, like some of them will have a little oxygen in them, for example, or straight CO2, which is a reactive gas, as opposed to the inert gases such as argon and helium. So understand that name, understand MAG, understand MIG. Then over in the next column, where it says, this is a bullet 2 for Flux-Cored arc welding, FCAW. Understand what those initials stand for. There'll be a question regarding that, both of those acronyms on your test. Then continuing reading here, it says, Flux-Cored arc welding process started gaining industrial use in the 1950s for the express purpose of improved metallurgical properties derived from the flux and the slag that supports the shape of the weld bead. Within certain flux-core electrodes, the need for external shielding gas is eliminated. Instead of the solid wire used for gas metal arc welding, a tubular wire is used for flux-core arc welding. That's a bullet. The outside of the wire acts as the electrical conducting sheath or the electrode and provides the bulk of the weld metal bead, and while the core contains the flux and other ingredients. Some of these electrodes generate sufficient gas shielding and are thus referred to as self-shielding. Now that is FCAW-S. So you remember what that S stands for. So that is a bullet. They act much like an SMAW coated electrode turned inside out. Since they generate their own shielding, the equipment is less complicated. A great deal of smoke, bullet, is produced due to the nature of high deposition capability as compared to shielded metal arc welding. Flux-Cored arc welding self-shielding is favored for work where the externally supplied shielding gases may be blown away and where smoke buildup is not an issue. A very common trade name applied to this type of electrode is inner shield, and that's what we use. Those of you, when we go through this class, if you look in there at all of the welding power supplies we have along that row, there's that big red one with a huge spool on it. That is a self-shielded inner shield brand of flux-core arc welding. It's very popular in the coal mines. They can go out there and they don't have to put any kind of a shielding gas around it because the high winds out there on the plains, it'll just blow that shielding gas away. So they may build some kind of a windbreak to protect, they call them a hooch whenever they build these little windbreak things. But they don't have to be as complex or as airtight as when they're using a shielding gas. The arc characteristics of self-shielded is an awful lot like stick rod. Like it says in your book here, you can just think of it as a stick rod turned inside out. And that's all it is. So the arc characteristics are an awful lot like this stick rod. So when you're welding with it, you may get magnetic arc flow and the other problems that you would encounter with stick rod. And just remember to change your gun angle the same way you would change your rod angle, and that will help you to compensate for a lot of that. Going on to your book here, it says, other flux-cored electrodes require an external shielding gas. These electrodes are referred to as gas-shielded, FCAW-G. That's another bullet. They typically run on DCEP, direct current electrode positive, that's a bullet, and have very good penetration and fusion characteristics. They also tend to have greater welder appeal and produce less smoke than the self-shielded type. A very common trade name for these electrodes is dual shield, and that's exactly what we use in our welding lab. So we use inner shield and dual shield, the same as they're mentioned in your book here. Now here on the board is a schematic of a gas metal arc welding system. It's similar to figure 21.3 that's on page 749 in your textbook, but this one, I like this one better because it shows more. Here we have a shielding gas in with a solid wire. When you're doing gas metal arc or MIG, it's a solid wire, not a tubular wire. We'll get to the tubular wire in a bit. And then you have a current conductor, shielding gas, so you have three things coming in. And direction of travel, he's pulling this along like so. A wire guide and contact tube, then a gas nozzle, a shielding gas, then the welding arc, and the filler metal, of course, is consumable. Here's your base metal, and then your weld metal here. And sometimes when you take tests, you may get a picture like this, and you'll have to recognize what this welding process is simply from the picture. So study the picture in your textbook. Also look at this. And look for visual cues that will tell you what type of a process this is. Well, we can tell that it's a semi-automatic process that produces a shielding gas, or a gaseous shield, and it has a gas coming in with a solid wire. Those two cues alone should pretty well point you in the direction of this being gas metal arc welding. So look for these visual cues so that you can recognize what type of a welding process this is simply from the picture. Let's see, go ahead and flip the page to 750. In the first column it says, gas metal arc welding frequently replaces another joining process such as riveting, brazing, silver soldering, or resistance welding. Those processes are used, some are used greatly, and some are used not so much anymore. If you read here, it also says it may be used instead of the following fusion welding processes: oxyacetylene welding, shielded metal arc welding, submerged arc welding, Flux-Cored arc welding, and gas tungsten arc welding. So you might use it in lieu of those other ones. And in particular, oxyacetylene welding, it's got a long ways towards replacing oxyacetylene welding. A lot of other colleges have taken oxyacetylene welding completely out of their program because it's more or less obsolete. We've reduced the number of booths that we have in there. I think we have 5 now. When I started here 14 years ago, we had 9 booths. So we have de-emphasized it because it's really not, oxyacetylene welding simply isn't that popular anymore. I mean, it's a nice little elective, but it's been, for the most part, replaced by gas metal arc welding. So, advantages. Look in that column, you'll see some of the advantages. Well, here, before we get to that, take a look at this slide here I put up on the board. Now, your book has pictures of power supplies and wire feeders and so forth, all of the equipment, but it doesn't show it all combined in one unit. This picture here shows all of the stuff combined, and in a workstation. It's all set up and ready to work. So here you can see your manifold coming in with all your different shielding gases. Here are some regulators. Here we have a bottle of gas with a flow meter. And we'll talk about flow meters later on. It says shielding gas regulator. Then your spool of wire. Of course, in the welding lab, most of our spools are covered. We put a cover over these things so you don't get dust and such on them. That dust and such that you can get that will settle on these wire spools can be dragged into the wire feeders themselves and clog up the liners. Here it's plugged into its power supply. Here it has its control panel. Now this is a full-size transformer type power supply, and we use high-frequency inverters, so they're a lot smaller, and they produce just as much electricity and amperage. This happens to be a 400 ampere power supply. Ours are 300 amperes. You have a welding power source and the controls, a work lead piece, cable assembly, which is your gun, and then a table clamp. So if you were to look at this picture and try to recognize what type of a welding process it is, Your cues would be the spooled wire, your filler metal, then a wire feeder, then a gun, and really the gun is pretty much a giveaway. And then seeing this gas supply back here would be another giveaway that this would be gas metal arc welding. The final thing is the gun, because this gun is going to be shaped a little bit differently than the Flux-Cored arc welding. We'll look at some Flux-Cored arc welding equipment later on. Well, here it is, Flux-Cored arc welding. This is a picture of the self-shielded type of Flux-Cored arc welding. This is similar to figure 21.5 in your textbook. In fact, I think it's the same picture, 21.5, and that's on page 750. If you look at this self-shielded Flux-Cored arc welding, we have a wire guide and contact tube. Here's the solidified slag, molten slag. We have a tubular electrode. So that by itself tells you that this is not gas metal arc, because in gas metal arc we use a solid electrode. Powdered metal, vapor forming materials, deoxidizers and scavengers, that's on the inside of our tubular electrode. The arc shield composed of vaporized and slag forming compounds. So the shield is what protects it protects the molten metal from atmospheric contaminants. Arc and metal transfer is occurring here. Here's your weld pool, your weld metal, and they're moving along like so. So again, be able to look at this and tell from the picture what type of welding process it is. Gas metal arc welding advantages, and these advantages are listed on page 750 and 751 in your textbook. They will be on your test. I'm going to ask you to name a couple of those advantages. So study them in your textbook, but if you want to write off in the margin these, it might behoove you to do so. It'd be easier for you to look at those. Gas metal arc is a semi-automatic process. It produces high productivity. There's no slag to remove. It's a clean process. A continuous filler metal process, so that you don't have any stubs left over that you're going to waste material. It'll weld most alloys. It's also easy to learn, and it's one of the cheapest processes out there. So those are some advantages of it. Now, I don't know that your book really covers limitations, but we're going to go over them real quick because you need to know this. What are the limitations? All welding processes have advantages and limitations, and they all have inherent problems. So the limitations are, you can't use it in windy conditions. That's why I spoke about hooches earlier. You'd have to have a hooch built around you if you were outside so that your gas's shield isn't blown away. Little tolerance for contamination. You should be cleaning your parent metal, cleaning all the rust off of it, all the oxides off of it, all the mill scale off of it before you weld. Take it down to clean white metal. It's usually limited to shop welding, and actually about 70% of the shop welding done in the United States is done using gas metal arc welding process. The equipment is somewhat complex, and then you have other consumables besides the filler metal and gas, consumables such as liners and contact tips. Those things will get used up after a while, and they have to be replaced. Let me go back to that one real quick. Make sure you understand these 5 things. Now, again, write this off in the column someplace, and I'll give you a minute to do so, because you may be asked a question about limitations. I may ask you to name a couple of limitations. And again, it may not be in your book, but I want you to know them, so write this down. Discontinuities. By this time, everybody should know what a discontinuity is. You've been taking enough classes. The difference between a defect and a discontinuity is that a discontinuity is an interruption in the weld metal, any interruption in the weld metal, and that becomes a defect if it exceeds acceptance standards. So some of them are porosity, incomplete fusion, which is a big one, and incomplete joint penetration. Again, write those down. I may ask you to name one discontinuity that is associated with gas metal arc welding. Okay, let's see. If you'll turn the page, forms of metal transfer. This is in your book. Reading from the second column on page 752. I'm reading the last paragraph, right above where it says open arc transfer. It says, in gas metal arc welding, filler metal is transferred directly through the welding arc. There are two basic types of metal transfer. Bullet, open arc method. Now the open arc method consists of any of them that, anything other than short circuit transfer. And in the open arc method, the molten metal is separated from the welding electrode, move across the arc gap, and deposited as weld metal in the joint. In the short circuit method, the weld metal is deposited by direct contact of the welding electrode to the base metal. It actually shorts out. Now, of these open circuit types, there's three, and this slide shows the first one, spray arc transfer. So that's a bullet by spray arc in your textbook. Essentially, what spray arc is, as the name implies, you're going to use high amperage and special gas. You're going to use a 90% argon, 10% CO2. You can use other combinations of gases, but this one works pretty well, and it's also the one that we use. It's called 90-10. And what it does is it energizes the high amperage in gas, energizes the arc area, and your transfer occurs as droplets. And this is one of the processes we will teach you in this class. And when you do it, you'll see that it comes off in a spray. And of course, that's where it gets its name. It's only suitable for welding in the flat and horizontal positions. Make a note of that. You can only use it in the flat and horizontal positions. And it has deep penetration, because it's the most energetic of all of the types of metal transfer that we're going to talk about. So again, be able to look at this and recognize this as the spray transfer method. Next we have globular. This is on page 754. I want you to read about this. Now, globular doesn't use quite as much amperage as spray does, and its transfer mode is denoted by the fact that the droplets will form to a larger diameter than the welding metal. And that's how you can tell. They'll come across there, they'll jump across this arc space here, and the droplets will always be larger than the diameter of the welding rod that you're using. Now, we're not going to teach you this, but you need to be aware of it. It gives you better arc control, and so you can weld out of position with it a little bit. It also has a kind of a sputtering sound whenever you're doing it. So globular would be the next one. Read about that in your textbook. There'll be a couple of questions on your test about these different spray transfer methods, and you need to know them. So spray and globular and pulsed arc. These are all open circuit modes of transfer. That's what the topic started off with. All three of these are those open circuit type. Or pardon me, open arc type. And this is the last one. In pulsed arc, the welding current is variable. It is pulsed between high and low current cycles, which are set by the welder. Some machines allow you to set that. Some are pre-programmed into these machines. These little inverters, you can actually call the factory and say, we're going to be welding this to this. We want to be able to use pulsed transfer, and the company will actually set those things in a memory chip for you, and all you've got to do is punch a button and it'll be ready to go. So pulse transfer is the other one you need to know, and you can actually weld overhead with this. Benefits are it gives you greater depth of penetration. You can weld in any position with it. And a term you need to be familiar with is peak or dwell time. When you're doing pulse transfer, this is what the cycle is going to look like, and you can see this in your book. Now your background amperage might be 50 amps. But then it's going to ramp up to your welding amperage, which might be oh, I don't know, 200 amps. And then it will stay there for a set time, and that's called your dwell. So be familiar with this. Sometimes it's also called peak. So be familiar with that. Read about that because you may get a question to the effect of which spray transfer method uses a peak amperage and a dwell time. What these terms? What are these terms associated with? Which type of a transfer method? So be familiar with that. Read that in your textbook. And then finally, we have the short-circuiting transfer method, which is what you're mostly doing. You're using the short-circuiting transfer method, and if you look at these pictures, they're very similar to the one that is in your book. I think this slide's a little bit better. That's why I like to use it. And let's see. Look on page 756, figure 2115, and it's similar to what I've got up on the board. And in the short-circuit transfer mode, a drop begins to form on the tip of the electrode. The drop advances towards the base metal. The drop touches the weld puddle, causing a short circuit. And then the pinch force that you'll read about causes it to pinch off, and then the circuit is broken whenever it pinches off, and then another drop begins to form. And this happens continuously. Of course, so fast that you're not aware of it. The thing about short-circuit transfer is that, and please remember this, write it off someplace on the side of your book, it has the lowest amount of heat input of any of the gas metal arc welding processes. It is also one of the lowest heat input processes of any of the welding processes out there. So that's very important to remember about short-circuit transfer. If you don't know the proper techniques, your welds can fail due to lack of fusion. Okay, so study figure 2115 in your textbook. So you should have bullets by open arc method, short circuit method, spray transfer, globular transfer, pulsed arc. And on page 755 where it says short circuit transfer, GMAWS, you should have a bullet there. Know the difference between, know why, because there is no metal transferred across the arc in the short circuit because it actually touches the metal. On page 756, understand what pinch force is. Pinch force. Okay. And let's see what's next on our slides. Factors for transfer modes. What's involved? Well, I already mentioned that with spray, you've got to have a 90% argon, 10% CO2. But for short circuit, you can use 90-10, but you get better arc characteristics if you're using 75-25, 75% argon, 25% CO2, which is what we're using in the welding lab. So shielding gas plays a critical role in the type of metal transfer. It helps with arc stability. It can affect the amount of spatter. It can affect the amount of deposition, how deep into the weld pool you're going to go, how deep into the base metal, and it can affect the amount of heat transfer. So shielding gas is very important. Current level is very important. I've already mentioned that you're going to use a high amperage with spray, but you're going to use a low amperage with short circuit. Voltage level is important, and what type of a power supply you're using in terms of DC-EP, DC-EN, or AC. Those are all important factors that influence metal transfer. Let's see. Go to page 757. Under constant voltage characteristics, that's the type of power source you're going to be using. It's a constant voltage or constant potential power source. Now this is a volt-ampere curve based on a constant voltage power source. You have a couple of pictures of some in your textbook. Figure 2117 is is one, and then over on the next page, figure 2118 is another one where they've superimposed a drooper with a constant. And if it's constant voltage, what it means is that the voltage is going to stay virtually the same no matter how you increase the amperage. In a constant current, it's exactly opposite. The amperage will stay about the same no matter what you do with the voltage. So for doing semi-automatic and automatic welding processes, you're going to use a constant potential power source. Remember the name, constant voltage, because that will be on your test. Constant voltage. It's a constant voltage power source. So here you can see we start out at 30 volts, and at 100 amps, it's dropped down to 25 volts. But then at 200 amps, we've only lost 5 volts of power. Only 5 volts of power. You've got just about that much in your flashlight. Then at 300 volts, you've only dropped down to 15 volts, 300 amps. So you can see there's only a 10 volt difference between 100 amps and 300 amps. So it's virtually unchanged. Such a small amount of change. That's why they call it a constant voltage. No matter what you do with the amperage, the voltage is going to stay about the same. Important thing to remember on that. So read about constant voltage power supplies and their characteristics. On page 759, first column, highlight this. The volt-ampere curve of the constant voltage power source used for gas metal arc welding has a relatively flat output slope. Figure 2117b shows that. Small changes in the arc voltage result in relatively large changes in the welding current. Figure 2118 shows that when the arc length shortens slightly, a large increase in welding current occurs. This is a bullet. This increases the burn-off rate, which brings the arc length back to the desired level. So when you're welding, you know it's going to sputter some on you. And then you get that gun in there just a little bit closer and it stabilizes. And that's what the machine does. It kind of senses whenever you're pulling it away, and it's still going to try to compensate for you doing this with the gun. And it's the same thing with stick rod welding. Remember, you kind of control the heat and put a little bit with stick rod welding by moving your rod in and out. Same thing here, but the machine is trying to compensate for those little discrepancies that you make. And this explains exactly why they do. The constant voltage power source puts out enough current so that the burn-off rate equals the wire feed rate. If the wire feed rate is increased, the power source puts out more welding current so that the burn-off rate and the wire feed rate are again in balance. So your amperage, essentially, as you turn up the feed on your wire feeder, the power source is automatically going to increase the amperage to burn off that additional material that you're dumping into the weld. That's why it's always best to go ahead and you set your voltage first, and then you dial in your amperage. And you just listen for that high humming sound. And when you get that high humming sound, you know you've got everything in balance and everything's looking good and running good. And if you have to go hotter, if it's not hot enough, you don't think you're getting enough depth of penetration or enough fusion, then start by turning up your voltage. Just crank that voltage up 3 or 4 volts. Doesn't take much. Just like our volt-ampere curve shows, it doesn't take very much. Just crank it up a couple of volts, 3, 4 volts, and then dial it in again. Just pull the trigger, run a bead, and listen for that humming sound, and slowly increase or decrease your wire feed as you need to get that humming sound, and bring those two things back into balance again. And the machine will do the rest. It'll balance it out for you. Okay, let's see. Type of controls. Right there where it says that, highlight right, well, let me just read it. It says all constant voltage machines have voltage control. Open circuit voltage on these machines is lower than on a constant current machine. The maximum is usually about 50 volts open circuit voltage. Remember that we abbreviated that OCV, open circuit voltage. So on these semi-automatic processes, the maximum is about 50 volts. But if you'll remember, our open circuit voltage on our constant current power supplies was about 80 volts. So you can see it was a little bit higher. Now whenever you close the circuit on this, in the case of gas, metal arc, or Flux-Cored, when you pull that trigger and start that welding arc, that's when this is going to drop down to 16 volts or 19 volts, whatever it is you've got it set at. And when we were doing stick welding, that's when this would drop down to 22 volts or 27 volts or whatever. So that would be our closed circuit as opposed to our open circuit. So remember that OCV means open circuit voltage, and also remember that the open circuit voltage is going to be less with a gas metal arc power supply than it is with a stick power supply. So once the voltage has been set, the machine automatically maintains an arc length while the electrode wire is fed continuously at a set speed. Changes in the filler metal, shielding gas, or granular flux may require a voltage adjustment because you're adding different types of elements, different masses involved with these elements. You may have to change that slightly to compensate. Self-regulation of arc length is possible because small changes in voltage cause the machine to produce large changes in welding current. Thus, any change in arc length results in a large change in current and a corresponding almost instantaneous change in the burn-off rate of the electrode. This regulates the current at the arc. Okay? So that's a bullet. Understand the burn-off rate and how that happens. Okay? Excuse me. Next, flip the page. Under voltage controls, they've listed a number of items here. There's three that I want you to pay attention to. The first one is voltmeter and ammeter. These meters permit accurate, repeatable selection of weld current and voltage. Then drop down to fine voltage adjustment. The hand control on the panel of the welder provides infinite fine voltage adjustment within the range selected. Fine voltage changes can be made while welding. And when I'm setting my machine, sometimes I'll reach out there and change that, but typically I'll set the voltage first, and I'll reach out there and change my amperage. But you can do it the other way too. You can set your amperage and then dial it in with your voltage. I've just found it easier to do it with the voltage by presetting the voltage. But even once you've got it preset, some machines have a fine tune to where you can just dial it in and get it down to just as perfect as you can possibly want it. So this permits the operator to obtain exact welding settings under welding load conditions. When they talk about under welding loads, that's when you're just sitting there and the machine's running and you're down to your closed circuit voltage and all of that. You can just fine tune it. The other one I want you to put a bullet by is contactor control receptacle switch. Now, provisions are made for a 2-conductor lead from the wire drive control of the contactor control receptacle. This completes the circuitry necessary for remote control of the welding power. The actuating mechanism for closing the circuit is the gun trigger switch. When it is closed, the primary contactor in the power source is energized and welding power is available. Well, that's a mouthful. What's it mean? Let me show you here. This is a brand new welding gun, and this is exactly like the welding gun you're using. And what we've got here is your gun. Whenever you pull the trigger, the wire starts feeding. What else happens when you pull the trigger? Well, the gas is going to start flowing. Why is the gas flowing? Because once you've closed that circuit, an electrical impulse is sent to a solenoid. And it tells that solenoid, okay, open up so we'll get some gas. And it also sends a signal to the motor. It says, all right, start pumping out some wire for us. So a lot of things happen whenever you pull that trigger. And that trigger is connected to the power supply through this. And the power supplies that you're using now, this is really a great design. It's a big improvement over what they used to have. You can see it's hardwired in here. But there's only 2 leads. If I wanted to, I could take and short these out. I could cut this thing, bare those wires, touch them together, and everything would start running because that's all the trigger does. It just closes the circuit. And that's why they only have 2 leads, an in and an out. Completes the circuit. And you can see you can't really pan in there to see that, but there's 2 little probes there, and that's all that you have to complete the circuit. Now, I say this is a big improvement over the other system that they used to have, and you're going to probably run into that other system quite a bit in your careers. And this is the other system. This is the old type. And we still have a couple of machines that have this old type. And if you look at the end of that, there's just 2 little metal probes there, and this thing just slipped in at the base of the gun to complete the circuit. and the other end would then plug into the wire feeder like so. But again, it's just two wires, and all you're doing is closing the circuit with it. I could take a piece of TIG wire and bend it and stick it down in there, and again, I could close the circuit and make that run. So these were not nearly as good as the new ones. And if you're ever having a problem, for some reason your gun stops working and you don't know why, this is the first thing you check, because these things are notorious for falling off, for breaking, or for not making connection. So that's just a heads up to you. In the real world, you could have problems, and this is the first thing you check, is where this thing ties into the gun. Okay? And then also, if we don't cover it if I don't read it out of the book or you don't find it, remember that when you pull the trigger, three things happen. You initiate this solenoid, which makes the gas flow start. You energize the system so that you have welding amperage available, and you kick that motor into gear. Okay? So a lot of things happen when you pull that trigger. And if this thing isn't making good contact, nothing's going to happen. Okay, let's go back to your book. Next page, 761, current controls. There is no current adjustment dial on a constant voltage unit. Current is adjusted by the wire feed speed setting on the wire drive unit, which is what I mentioned earlier. As you increase your wire feed speed, the power supply automatically increases amperage to burn off, melt that additional mass, that additional material. Slope controls. Slope controls the amount of current change. It is caused by an impedance to the current flowing through the welding circuit. And then in parentheses it explains to us what impedance is. Impedance means the slowing down of a moving object. What it will do is it will slow down the change in the electrical power supply being supplied. It says, since voltage is the force that causes current to flow but does not flow itself, the impedance is directed towards limiting the flow of current. It is not intended that the current be stopped, only limited. As more impedance is added to the welding circuit, there is a steeper slope to the volt-ampere curve. The steeper slope limits the available short circuit current and slows the machine's rate of response to changing arc conditions. Constant voltage DC transformer rectifiers are available with fixed slope or variable sloped types. So you can have a fixed slope machine, and these are the only things I want you to remember here. Fixed slope machines and variable slope machines are the two types. And then go ahead and flip the page. Inductance controls. Inductance controls the rate of current change. This will affect arc starting. Adjustment of inductance is most common in the short arc gas metal arc welding to control weld spatter and how fluid the puddle is. Fixed inductance is common on many constant voltage machines, and no further adjustment is normally required. Variable inductance may be tapped or continuously variable. Controls are similar to those used for voltage and slope. I like this little bit they tell us here. It says inductance can best be understood if you consider the constant voltage volt-ampere curve. Visualize what must happen on a volt-ampere curve when the arc starts. The welding machine must be capable of responding to the tremendous demand for current to burn the electrode free without overcurrenting and creating a blasting start, and without undercurrenting and creating a stumbling start. So when you pull the trigger, it just takes off right away if everything is adjusted right. But if it isn't, it's going to sit there and pop on you. There's some things you can do for that, but a lot of it is related back to this inductance, to get that all set just right so it'll fire up every time you pull that trigger. Consideration must be given to the arc length and amperage changes required during the short circuit mode of transfer. Keep in mind, the short circuit mode of transfer can take place at nearly 200 times per second. Bullet. As the energy moves along the volt-ampere curve, the speed with which it is allowed to move is controlled by the inductor control on the machine. Think about your ability to move through a room if the floor is dry. Then think how you would have to be slowed down if you were moving through several feet of water. And then if the room were full of water and you had to swim, think how much it would slow you down. And that would be analogous to having 100% inductance. So it inhibits the flow is what it does. So keep that in mind. That's the bullet. Inductance would inhibit the flow. And also keep in mind that short circuit transfer mode occurs 200 times a second. Some textbooks I've read will tell you 400 times a second, but I'll accept an answer of 200 times. Other controls, a weld timer most often can be added to the control panel of the standard wire feeder controller. It permits gas metal arc spot welding and other timed welding. We have a machine in there, a Lindy, that has just that control on it. You can set it for a quarter of a second or a half a second or a second or even 2 seconds. And you pull your trigger, and then wire is fed out for just an instant, and it creates a spot weld. Now the strength of a spot weld is determined by how big the spot is. So if you're only on for a quarter of a second, you might get a spot that's the size of the head of a pin. If you're on for 2 seconds, you might get a spot that's 3/4 of an inch across. But it takes a special gun, a special tip, to do spot welding. And this is one of those special tips. Now you can see it's got grooves. It's got grooves in the top there. And the reason it has grooves is so that you can take, when you're making a spot weld, you're going to join two pieces of usually typically thin metal like this. You're going to join them, they'll overlap, and you're going to join them together by burning through one and fusing into the other one. So you will take your MIG tip and you would just press it right down solidly on there. Pull the trigger, and you've already preset that timer that they're talking about for how long you want that to go. Quarter of a second, 1 second, whatever. And then it's going to flash, and it's going to come out, going to flash out all those little grooves that are cut in there. Light and smoke and sound is all going to come out. When you pull that away, you're going to have a nice little spot in there, you know, maybe about the size of a dime, and these two things will be joined together. Spot welds are great. Typically, the strength is about 800 pounds. We wouldn't be able to pull those two pieces of metal apart if we were to put a spot weld on there. We'd probably have to get a hammer and chisel and still not be able to get them apart. So spot welding is something that you should be familiar with. It's a very common practice, and that's what the timer control is used for. So that would be a bullet as well. I may ask you a question about spot welds. Flip the page. You're talking now about power supplies. It says types of constant voltage welding machines. Basically, I want you to know that there's three types. There's the transformer rectifier type. That's the bigger machines. The inverters, which are what you're using, and then engine-driven generators. These guys that pull in with welding trucks on the back of their, with welding machines on the back of their trucks, those are engine-driven generators. And then you can attach a high-frequency power supply like the ones you're welding on. You can attach one of those to those machines, and you can do gas metal arc welding off of one of those. So just three types. Transformer rectifiers. If you look at the MIG machines we have back there, I mean the stick machines we have back there along the wall, the big blue ones, those are transformer rectifier machines. They bring AC in. The AC is chopped in half through the rectifiers and through a series of diodes, and it produces DC. And so that's how they do that. And then the inverters, they take that and put it through high frequency and change it into the welding amperage that we need, and that's how they're able to reduce the size of those. And then we have the engine-drivens. Now I've got a bullet by each one of those. I want you to know a little bit about what those are, and I definitely want you to know that there's three types, and I may ask you for the name of one of those, or maybe even two of them. Okay, flipping the page, machine selection. I highlighted most of that first column, but I want you to put a bullet by paragraph 3 that says most MIG or MAG welding is done with DC electrode positive, which gives better melting control, deeper penetration, and good cleaning action. This is especially important in welding such oxide-forming metals as aluminum and magnesium. It says DCEN, DC electrode negative, is seldom used. Farther down, spray arc, bullet. Spray arc welding generally requires from 100 to 400 amperes for semi-automatic applications. 100 to 400 amps. So that's an awful lot of amperage for spray arc, but as I mentioned earlier, you have to have that higher amperage and a special gas to get that stuff to spray across there properly. Short circuiting process gas requires only 25 to 250 amperes, so there's a huge difference in the amount of amperage. And then Flux-Cored wire utilizes from less than 100 to up to 500 amperes in applications without shielding gas. That would be our self-shielding stuff. If you're using carbon dioxide shielding gas in automatic setups, the current ranges from 100 to 750. And then automatic submerged arc welding requires 75 to 1,000 amps. Well, everybody's probably seen our sub-arc machine in there. Our power supply only goes up to 600 amperes, so you're really talking some heavy amperages if you get on up there. So pay attention to that. One question will come out of those three items there. It will probably take the form of something similar to which one of these would require the most amount of amperage. Okay, wire feed control units. Read about that. I do have a bullet at the bottom of that column, particular figure 2137. If you look at figure 3127, this is what you're welding on. We have this same unit, only ours is slightly different. If you look at the face of this one, ours has dual control. So we have basically two of those units together so that you can have gas metal arc on one side and Flux-Cored arc with a shielding gas on the other side. This is a typical setup that you'll find in a lot of fabrication shops. So read about that, because I'm probably going to ask you a question related to that. Read what it says about figure 2136. So you want to read that first column where it says wire feeding control units, and then read about figure 2136, and then put another bullet by where it says on the next page, the portable feeder shown in 2138 is of the voltage sensing variety. It says most wire feeders are of the constant speed variety and work off of a fixed voltage such as 115, 42, or 24 volts. They have electronic control circuits and drive motors designed to work off of these set voltages to deliver a very accurate constant wire feed speed. Voltage sensing feeders are designed to work off of the open circuit voltage of the power source, and while welding, the load of arc voltage and the power source they can be much more simplified and compact in design than constant speed feeders. The basic voltage sensing feeder works directly off of the voltage being supplied to it. A high voltage will cause the wire feeder's motor to speed up, causing the wire to accelerate, and this will shorten the arc and lower the voltage. Since the feeder motor works directly off of the arc voltage, the motor will see less voltage and begin to slow down. As less wire is being fed toward the weld pool, the arc will get longer and the voltage will go up. So it's self-regulating. This is what they mean by the sensing thing. So if you get a question to the effect of how does a voltage sensing variety type machine work, you're going to tell me that it senses the amount of voltage, and if there's more voltage available, it will speed up to deliver more wire, and if there's less voltage available, it will slow down to deliver less wire. So that's basically what I'm going to want there. I meant to bring in some drive wheels, but I didn't, so I apologize for that. These pictures that you see on page 771 are real good. There's various types, and just pop open the doors on your wire feeders and take a look at the different types of wire feeders, wire feeder wheels. Some of them have 2 wheels, some of them have 4 wheels. Take a look at the one that we're going to teach you spray arc transfer on, and look at the difference in that wire feeder. There's just a variety of them. I do have a bullet here about pull guns. It says the pull type of drive is preferable for use with soft wires, and this is a bullet, soft wires such as aluminum and magnesium. We have a gun in there, and if you'll flip the page to 773, these are spool guns, but a pull gun is similar to this. It looks similar. It's geared. It's got gears up in here, and this one has gears too. But a pull gun has gears up in here, and it basically pulls the wire while pushing it from the wire feeder as well. So it's being pulled and pushed. And if you take a look at our aluminum MIG in the welding lab, you'll see a pull gun. So there's going to be a question related to that pull gun that you're going to have to know. Now this one here is a little self-contained spool, and you can see it's got gas coming in here, and then here's its cable. Here, this one is a little different, but it has gas and electrical coming in from this cable. But they both have a little spool, and that spool is contained. And this is a typical spool. You can see it's not very big, maybe about 4 inches across. This one happens to be aluminum. You can see how bright and shiny that is. We have a number of these. Unfortunately, we don't have a gun that will operate these, but I wanted to point it out to you because they're very common. They're in wide use, and this happens to be aluminum alloy 5356. For those of you that have taken, that have studied Chapter 3, you'll see that this is one of the main aluminum welding alloys out there. And this has to be used with pure argon. When we weld with aluminum, we'll weld with pure argon. So I just wanted to show you that, to show you that what's underneath that cover when they show you a spool gun. So we've got three types. We have a wire feeder that pushes the wire all the way through and it comes out of your gun, which you're using. We have a pull gun, which it will be pushed at the wire feeder and pulled at the gun. And then we have these self-sustained spool guns. So three different types of guns. So pay attention to that, because you're going to get some questions about these different types of wire feeders and guns. And we haven't even gotten to Flux-Cored guns yet, so we'll get to those in a minute. Let's see. Turn the page to 774. And I think well, I thought I had a picture of some guns, but I don't. If you look on page 2146, you see a variety of different gas metal arc welding guns. And you can see a spool gun in operation there in figure 2145. Under nozzles, many different types of materials are used for nozzles. You can get them in copper and copper alloys. A clean, smooth nozzle will allow easy removal of weld spatter. The welder should not roughen up or abuse the gas nozzle on the gun. This one that I showed you that we use for spot welding is just one example. Now, in all the time I spent working in fabrication shops, the way we would clean these is we would take them off, and then we would take a rat-tailed file or a round file, and we'd go in here and we'd just run around the edge like so to clean it. We'd clean everything off of there. And then there's two things that you can use to help to keep that spatter from building up. One is anti-spatter, and we have this stuff available. There should be some in your booth. If there isn't, you can ask Mary and we can get you some. And it's just a spray. Shake the can a little bit. Spray it in there like that, and then just dip it up and let the excess drip off. You don't want to get it over on your weld. It won't really hurt it, but I always had a fear of dropping liquid stuff in there. Typically it'll vaporize beforehand. Sometimes we'll spray around the outside, and also you can take this stuff and you can spray it on whatever you're welding, and that will kind of form a coating that will keep spatter from sticking to whatever it is you're welding. They also make a paste. It's a powder actually that you mix with water, and you can paint it on with a brush, and it creates a protective coating. The other thing that we have, and it's also very common, is a gel dip. Now this jar is pretty dirty and pretty messed up. Typically these jars are white and they have a nice little cap on them and they're labeled and all that. And you'll take your hot gun, you're just done and you've just cleaned it up, and you'll actually dip it in here and coat it. And once you've coated it, now that stuff comes out pretty gooey and pretty thick. So you want to sit there and let it drip off, let the excess run out of there, and then get over on a piece of scrap steel and run a little bit on scrap steel before you go and start your welding again. And that also is another way of protecting the cup from spatter. If they get clogged up, which they'll do, they'll clog up and they'll bridge from your contact tip to the cup itself. And if that happens and you touch it to metal, it's going to short out. So be aware of that. You've got to keep that clean, or else you're going to have problems with shorting, arc shorting, as a result. Okay. So under cable assemblies, cable assemblies are an integral part of the gun. They generally consist of a single molded conductor that encloses all the necessary components. The electrical wire is guided through a flexible liner contained in the cable assembly. The liner is made of spring steel for strength and protection. And this is a liner. And I always thought they kind of looked like brake cables off of a car, and they do kind of. And there you can see it just uncoils just like that. And your wire is fed in here, and then you simply feed this thing down the gun until it comes out the end, and you cut off any excess that you have. And the wire, of course, goes down through the middle of it. Now you can tell the size by reading right here. It'll be stamped in right here at the end, and this is a This is a 0.45. So this was designed to use 0.045 or 45 thousandths wire. You could also use 0.35 wire in that. The ones that we have in there, I think they're a little oversized, and that may be responsible for some of the spattering that you're getting. If it gets too big, they'll have a tendency to kind of hang up a little bit. So you want to match the size of the liner to the size of the wire you're using. You also want to match the size of the rolls. We talked about rolls a minute ago. You want to match those rolls to the size of the wire that you're using. Also, the guides that are in that wire feeder have to be matched to the size of the wire that you're using. So these things will get clogged up after a while. I talked about how we put covers over top of those rolls, over the spools of wire. That's to keep dirt from getting on there, because that dirt will get dragged in here, and after a while it will dirty up the insides of these, and they have to be cleaned. You can use a cleaning solution and blow them out with air and reuse them. And that's typically done to get as much life out of these. So these are some of the consumables that we talked about earlier. Besides the wire, these things get worn out and they have to be replaced, and they're kind of pricey. Okay. Next, let's see. Flip the page. I want you to read about that. I'm going to ask one question on nozzles. I'm going to ask one question on cable assemblies. And some of it may not be exactly what's in your book. Some of it may be about what I've been talking about. Okay, page 777, gas flow rates. In order to provide a good gas shield, the gas must be fed through the nozzle at such a rate as to ensure lamellar flow. Lamellar flow. That's a bullet. If the flow rate is too high, it causes turbulence, swirling. The turbulent gas shield mixes with the surrounding air under the nozzle and causes contamination of the weld deposit. If the gas shield fails to cover the arc or is contaminated, porosity results. Almost all porosity in the MIG-MAG welds is caused by poor gas coverage. Too much is just as bad as too little. Now, if you'll take a look at, let's see. Well, let's just turn that off. This is the same picture you have in your book, and I like this because it really illustrates well what we're talking about. Here we have a lamellar flow of gas, straight gas coming out, protecting the shield. But here you've got to you're trying to force too much out, and it's causing turbulence. And as you're causing that turbulence, you're sucking in air from the surrounding atmosphere and contaminating the weld pool. Same thing can happen when you're doing gas tungsten arc welding. So remember, lamellar flow versus turbulence. I may not ask you specifically what's a lamellar flow, but I may ask a true-false question to the effect of, is too much gas bad, or is too little gas bad? So be aware of the concept. Let's see. Top of the next column. Argon and carbon dioxide are much heavier than helium, bullet. The lower flow rates are required for equivalent shielding. The specific gravity of argon is 1.38 and the specific gravity of carbon dioxide is 1.52. Both gases, therefore, are heavier than air, and they blanket the weld area. So you may get a couple of questions there. You know, I may ask, is this heavier than air, or is this heavier than helium? Something to that effect, so know that. Dropping down to the bottom of the page, all those bulleted items. The following additional factors also have an influence on effective gas coverage, so read those. You may get a question out of that. And then that brings us to shielding gases on page 778. I highlighted that entire first column about shielding gases because it's got some good basic information. There is a bullet coming out of the second paragraph. It says, however, in the molten state, many of the metals absorb oxygen, nitrogen, and hydrogen from the air. These gases cause porosity and brittleness. The prime consideration when welding them is protection of the weld zone from atmospheric elements. Okay, we got to shield it. Highlight the last paragraph, which reads, the three principal gases for TIG and MIG or MAG are argon, helium, and carbon dioxide. Those are the three main gases. That's a bullet. If you look here at what I put up on the board, this is in your text. And we use short circuiting over 1/8 of an inch thick. The plate that you're welding is 3/8 of an inch thick. So transfer mode, short circuit. Recommended shielding gas, carbon dioxide, argon plus 15 to 25% CO2. So you can use either straight carbon dioxide, or what we use is argon and CO2, 75-25. And then it tells you advantages and so forth right here. You get less spatter if you're using an argon CO2 mixed, and better arc characteristics. So highlight that. Spray transfer is the other one right here. Spray transfer, argon plus 5 to 20% CO2. You've got to have that CO2 in there in order to get the proper transfer. You can still transfer with 75-25, but it's not as smooth. It's more of a sputtery, it's hard to describe. It just doesn't work as well as with 90-10. So we use a 90-10, 90% argon, 10% CO2, and then read about the advantages there. I may ask you a question of, well, which gas would you use for which type of transfer? Let's see. This is the next page in your text. This is page 780. I wanted to point out stainless steel right here. Now, you can use stainless steel to weld. Stainless steel can be welded with gas metal arc welding. However, because stainless steel has a lot of corrosion-resistant properties to it, it's got that chromium in there. We've talked about chromium before. And that chromium gives it corrosion resistance, and it also has some nickel in it. Nickel gives it resistance to high heat. So to melt it and to weld it properly, we have to generate more heat in the welding arc. So we do that by using helium plus 7.5% argon plus 2.5% CO2. So now we've switched mostly to helium. 90% helium, 7.5% argon, 2.5% CO2. Because helium is a better heat transfer gas than argon or CO2. Generates higher temperature at the weld puddle, and therefore we're able to melt that stainless steel, get better depth of fusion, and we can weld with it properly. And there's many different types of welding procedures that have been qualified using this. And it is called a trimix. I don't know if it's written in your book anywhere, but write that down in your column someplace, trimix. I may ask a question, what's trimix? And you're going to tell me it's a welding gas comprised of 3 different types of individual gases, and that would be helium, argon, CO2. That's a trimix. Or I may ask a question, well, what kind of metal or steel would you weld with a trimix? And you're going to answer stainless steel. Okay? Let's see. One other I wanted to point out is aluminum. Aluminum, you can weld up to 1/2 inch aluminum using the spray transfer or pulsed spray. And when we weld it, you'll see that it does kind of come off like a spray. And we use 100% argon. So I'm pointing these out because these are the ones that we use in our program. Okay? We use 75-25, we use 90-10, we use a trimix, and we use pure argon. Now, let me back up a little bit. We haven't done any trimix in a while, but it's one of the most common ones out there. I don't have any on hand right now, but we do get it from time to time. But know about stainless and that trimix. Okay, going back to your book. Read about argon, particularly paragraph 1, 2, and 3. Read about helium. 2 questions are coming out of helium, all in the remainder of that column. Okay? Be a couple of questions on helium. Carbon dioxide. Bullet in the second paragraph. Primarily, I want to know, why is it so popular? The answer I'll be looking for, because it's cheaper than any of the other gases. Okay? It's widely used in high schools because it's so cheap, but it can cause embrittlement because of the oxygen that's in it. So second and third paragraphs, you're going to have one or two questions coming out of there about oxidation effect and what are the advantages, what are the disadvantages. So read the second, third, and a little bit out of the fourth paragraph. Flipping the page, bottom of the second column on page 782, there is a considerable refrigeration effect. I wanted to point this out to you because this happens with both gas tungsten arc and gas metal arc. A considerable refrigeration effect in the high pressure section of the regulator. Sometimes on very heavy duty cycles, frost forms on the outside of the regulator. This indicates only that the regulator is getting cold. When frost appears, the small amount of moisture in the gas can form ice in the regulator and either stop the flow entirely or break off and be blown into the weld. In either case, porosity can and usually does result. So if you're out there welding and you're getting frost on the regulator, you've got to be aware of that. Now here's a regulator that I brought in for demonstration purposes, and what will happen is this whole body will get frosty. The glass will frost up on you, and it's simply because of when, of course, we're using compressed air. When that compressed air expands, it releases heat, and the changes in the tube pressure causes this thing to get cold. And if you're drawing it off too fast or for too long a period, it's going to frost up on you, and that can happen. Let's see, there's something else I wanted to tell you about regulators, but I don't think we're quite there yet, so we'll come back to this little item. Flip the page. On page 784, there's a bullet at the bottom of the first column. The shielding gas or gas mixture is an essential variable for most welding procedures. I've talked about essential variables before. I want you to understand, I may ask that question. I may ask you to name an essential variable associated with this. So that's the question, the answer I would want. The mixture cannot be indiscriminately changed without consulting the engineer responsible for the welding procedure. For students learning in an experimental environment, trying various gas mixtures is a helpful learning tool. However, in production, welding to a welding procedure, the welding procedure must be followed. If I were to change that gas, I've changed an essential variable, and so I've got to write an entirely new essential variable welding procedure that would address that change. So you may get something. If you see those words, essential variable, coming in there, that's a heads up. So I won't throw any curveballs at you, but it'll be something out of that paragraph I've just read. Argon and carbon dioxide mixes. Read those first two paragraphs, and then helium, argon, and carbon dioxide. That's our tri-mix. Read about that. Then finally, I have one more overlay. This is also in your text. Not only does it affect the amount of heat transfer, but it affects the amount of penetration. Penetration into the base metal. If we use pure argon, you can see we get really deep penetration. Helium, the penetration is a little more shallow, but it's broader. In a combination, we kind of get the best of both worlds. Argon and CO2, you can see it's a little narrower and not as deep. And here they're showing undercut with pure argon. Well, that can happen if you're using just pure argon. That's why we use 75-25, because that'll help eliminate the undercut. Pure CO2, you get narrow and deep penetration without any undercut, but CO2, of course, causes a lot of spatter, and it can cause oxidation or embrittlement along the edges. And then if you use argon, and here, look at here, oxygen, a reactive gas. And then you can see the weld puddle is entirely different from any of the other ones that we've seen. Shallow penetration, deep at the point of contact, no undercut. They'll use oxygen in very small amounts. 1 or 2% is about it. And again, that's more of an exotic type of welding. We don't, in my career, and I've been at this 27 years, I've never used argon and oxygen. It's something beyond my experience. Okay, let's see. Electrode wires. Well, real quickly, you can see my slides aren't exactly in tune with your book. That's because my slides are probably a little bit better than what is in your book. If you look here now, we know that this is a Flux-Cored arc welding procedure, but this picture is identical to the one I showed you before. So how do we recognize the difference? Look at the spool. It's a spoked spool. So if you looked at the picture, you would recognize this as being a Flux-Cored arc welding process, because that's the way the wire comes with Flux-Core. If it were a solid wire, we would have a solid spool. Okay? So that's, everything else is the same. We have our gas, so we know that if it's Flux-Core and we have a gas, we know that it's gas shielded or dual shield. Remember that name, dual shield. Now here's self-shielded. Okay, now take a look at the gun. The gun's different. It's long. It's got a heat protector shield for your hand. And this one has a solid spool, not like the gas protected ones. So we've gone back to a solid spool, but we know that this is self-shielded Flux-Core because there's no bottle. There's no gas bottle anywhere. So again, look at the pictures and learn to recognize from the pictures what process it is. So we've got gas metal arc welding, Flux-Core arc welding with gas or dual shield, and then self-shielded Flux-Core arc welding. Okay, the advantages, write this off in the side of your text someplace. Advantages of Flux-Core arc welding: high productivity, deep penetration, tolerates contamination because it produces so much energy, it'll burn most of that crap out of there. Suitable for field work. So write those down. Limitations. You've got to take the slag off. Remember, the arc characteristics are an awful lot like stick rod, so it's going to produce slag. You've got to clean it all off of there. You've got to make sure that you're not trapping any of it, so you're going to buff it off, brush it off, get it all out of there. Very smoky. Smokiest of all the processes I've ever been around. The electrode's a bit expensive, and the equipment is somewhat complex. So those are the limitations. Discontinuities. If you don't do a good job cleaning, you can have slag inclusions. Porosity can be a problem. Incomplete fusion can be a problem. You could get overlap on a bead. And if you get overlap, of course, you're going to have lack of fusion. Typically, this isn't such a big problem with Flux-Core because it does produce such a huge amount of heat and depth of penetration. But if you use an improper technique, it could still happen. And then incomplete joint penetrations. Typically, you'll use Flux-Core with a backing strip or a back weld, and that eliminates this problem. Okay, that brings us to our electrical wire. Okay, look on page 788. I've got some bullets here. At the top of the first column, it says the specific type of filler metal is selected for the following reasons. Why would you choose a particular filler metal? Probably the most important one is that it's got to match the composition of the base metal. Okay? Then after that, you want to control various weld properties to deoxidize the weld and deoxidize the weld deposit, to promote arc stability and desirable metal transfer characteristics. And then wire composition usually matches that of the base metal being welded. That's a bullet. I think that's the number one reason. Number one reason you have to match the mechanical properties of the base metal with whatever type of filler metal you're using. Number one reason. Highlight the first part of the second paragraph. There's a bullet coming out of here. It says, in addition to the alloying elements used in filler wires, deoxidizers and other scavenging agents are nearly always added. This is to prevent porosity or damage to the mechanical properties of the weld metal. When welding steel, some shielding gases such as carbon dioxide cause severe oxidation. Losses of alloying elements across the arc. The oxidizers most frequently used in steel filler wires are manganese, silicone, and aluminum. The question I'm going to ask here is about the alloying elements. The fluxes used are intended to replace that stuff so that you can come up to the properties of the base metal. So there'll be a question out of there. Deoxidizers, I'm not really going to ask you about deoxidizers, but the whole purpose of the alloying elements is, again, to get back to matching the mechanical properties of the base metal. So if I ask you a question to the effect of why would you want to put alloying elements into the filler wire? Well, to match the mechanical properties of the base metal. Flux-Cored arc welding, know that the S means it's self-shielded. The G means it's dual shield or gas shielded. Over on the next page, bullet, the flux is primarily a method of carrying the alloying and deoxidizing elements to the weld. This is less costly than providing these elements through the sheath of the electrode. Flux-Cored wire provides the following advantages over stick electrodes. So read those advantages, but the primary question I will probably ask you is, in a Flux-Cored wire, is the alloying elements in the outside wire itself, or is it in the flux? Okay. Okay, that brings us to page 791 and our slides. Read this, know this. The electrical identification system is slightly different from the shielded metal arc one because the wires are different. And it took a number of years to develop this. But again, similar to the stick rod, the E still means electrode. The R now means rod. So electrode, rod, and also you can get the same thing for TIG. It'll start out the same way for TIG. The next two numbers are for the strength, and you may be asked on this. Strength. S, solid wire. That's what the S means, solid wire. And then finally, the chemical composition of the metal. And we typically use either ER70S-3 or ER70S-2. Look both of those up in your charts, highlight them. I've got them highlighted in mine. And you may get a question on those. Okay. Flux-Core. Flux-Core arc welding identification system. Again, E stands for electrode. Now you see there's no R in there now. The very first number, not the 2, but the first number is strength. Second number is position. It'll be a 0 or a 1. A 0 or a 1. Tubular. Remember, with solid wire, it had an S for solid. T for tubular. X, chemical composition and operating characteristics. Exactly the same as with stick rod. That last number in stick rod in 6010, the 0 means chemical composition, operating characteristics. Exactly the same as 7018. The 8 means chemical composition, operating characteristics. Here that suffix, that last number, is going to be chemical composition and operating characteristics. Okay, let's wrap this baby up. So on page 792, read and understand what ER70S-3 is. Read and understand what ER70S-6 is. On table 2115, highlight ER70S-3, ER70S-6. On page 794, highlight EXXT-1, EXXT-1M. On 795, EXXT-9, EXXT-9M. And then on 797, highlight EXXT-9 and EXXT-1M. And then on page 798, EXXT-9 and EXXT-9M. Those are all wires that we use. And I think you'll find that all of those designations are almost identical. But read about them. And I think that's about it. I know that was a long chapter, but gas metal arc welding and flux-cored arc welding, the theory behind it's, there's an awful lot of why for behind it, beyond what you guys are doing and guys and gals are doing in the lab. You're learning the techniques there, and what's in this chapter are why those techniques work. So if you have any questions or I didn't explain anything properly, you know, it's a big field, and I still haven't covered everything. I know I tend to run on some, but there's so much important stuff that you need to know. So if you have any questions, just get with me or with Jeff, and we'll do our best to explain it.